Okay, so hello everybody. Let me remind you where we are, more or less, in our discussion. In the first lecture, we discussed the phenomenon of irregularities in uniform distribution. This is the situation when you look at the error term in Weyl's equidistribution theorem, the error term itself does not fluctuate evenly around zero. It exhibits some bias. It doesn't always happen, but it can happen, and it can happen at different degrees of severity. We discussed three forms of bias. The most severe one is sign bias, when the error term always has the same sign. This happens, for example, for square root of 2. Then there is what I call global bias. When you look at the histogram of the first n terms of the error term, you plot the histogram, it looks like a Gaussian distribution, but this Gaussian distribution is off-center. There is a drift. And then we discussed the more subtle form of bias, local bias. This is a situation when the error term prefers some possible values to other possible values. We even discussed the possibility of having exponential local bias, which is a scenario when you have two possible values, eta 1 and eta 2, for the error term. The frequency of seeing eta 1 is exponentially bigger than the frequency of seeing eta 2. Okay? So these are the form of bias that we described. I stated for you three results, one by Boschernitsan and Ralston, and two by Dmitry Dolgopyat and I, which characterize the alphas for which you see this bias for the interval 0, 1/2. And then we started to discuss the proof of the second two results, okay? Those that were not done by Boschernitsan and Ralston. Now, the way that we did this was, in the second lecture, was to restate the problem as a problem in dynamical systems. And what we saw is that you can study the behavior of the histogram of the first n terms of the error term by examining the Birkhoff sums of a certain skew product over irrational rotations called the cylinder flow at a particular initial condition. So I would like to emphasize that the dynamical problem is not an almost everywhere problem. It is a problem of understanding the asymptotics of Birkhoff sums at a particular initial condition. And then I mentioned to you, I recalled the beautiful result of Hooper, Huber, and Barak-Weiss, that you can view the cylinder map, you can think about the cylinder map as of the Poincare section of a linear flow on an infinite surface that looks like this. Moreover, the roof function is constant, and therefore, instead of analyzing the Birkhoff sums for the cylinder map, it is sufficient, it's equivalent, in fact, to analyze the Birkhoff integrals for the linear flow. And this is very useful because the staircase where this dynamical system acts has many, many symmetries, okay? Just like the torus has many, many automorphisms. For every matrix in SL to Z, there is an automorphism. Something almost as good happens on the staircase. Here, every matrix in gamma 2, so SL to Z, odd on the diagonal, even off diagonal, can be realized by an automorphism. And we discussed the fact that if you have, if the direction of motion is what corresponds to an angle of bounded type, then you can construct a sequence of automorphisms which shrink the direction. So the idea is to start with this very, very long orbit for the linear flow and simplify it by contracting it to an orbit of length much smaller than 1. Why is this good? Because short orbits do not have a chance of winding around the staircase, so they are very easy to understand geometrically. Then we saw that in order to understand the Birkhoff sum, using the method of symbolic dynamics, the problem reduces to understanding probabilities of this form. Okay, so what do we have here? We have a Markov chain, okay, xn. We have jump functions, which model the jump in the z coordinate on the translation surface due to each of these automorphisms, okay? Sn is the sum of the jumps. And basically, the Birkhoff integral that you need to examine boils down to, up to some approximation and some wiggling, boils down to expressions that can be written in this form: the probability that Sn, the sum of the jumps, equals a particular value given something. Okay, now what is this all-important particular value? That's the most important part of this formula. It is, in our case, the z-coordinate of the rectangle which contains the image of this line. Okay? So this is the most important parameter in the problem because this is the one which is most sensitive to the initial condition. Okay? If I had moved my initial condition just a little bit, then these are chaotic, these are uniformly hyperbolic automorphisms. The result would have been at a completely different part of the surface. So this is extremely sensitive to the data of the problem, and that is why we need to deal with it with extra care. Okay, that's all the number theory in some sense. All the number theoretic behavior sits inside the way this sequence behaves. Now, what I would like to do today is to explain to you some ideas in how to find the asymptotic behavior of these probabilities. Okay? Now, before I do this, I would like to mention one thing. I told you that we need to use a sequence of different automorphisms to do the renormalization, to contract the direction. There are some blessed scenarios when you can take all those automorphisms to be equal. Okay, this is the case when the direction of motion is exactly the eigendirection of a hyperbolic automorphism. By the way, guess what? The angles which exactly have this property are the quadratic irrationals. Okay? If this is the scenario and you can use exactly the same automorphism, then the Markov chain that you get in this reduction turns out to be homogeneous, stationary. Okay? Because you're using the same job at every process. And then understanding probabilities of this form falls into what's called the local limit theorem for homogeneous Markov chains. Homogeneous Markov chains. And the tools for doing this were developed in the 50s by Nagaev. As we saw in the talk of Richard Sharp, generalizations to equilibrium measures and Helder continuous potentials appear very naturally and very importantly in ergodic geometry. And there, the version of the LLT is due to Givarch and Hardy. Okay, this is the case when you have a quadratic irrational and you can take the same automorphism. But there are only countably many quadratic irrationals. There are uncountably many bounded types. So for most angles of bounded type, you're not going to be able to do this with a single automorphism. You need to use different automorphisms. And then, alas, everything is going to depend on n. Okay? The state space of the Markov chain are going to depend on n because instead of a single Markov partition that works for all automorphisms, you have a sequence of Markov partitions, one for each automorphism. The transition kernels depend on n because you're using different dynamical systems. Okay, different automorphisms. And the jumps are going to depend on n. Okay? So you fall inside the inhomogeneous setup, and this is an essential feature of the problem. Okay? So what I'm going to tell you today, or discuss today, is how to find the asymptotic behavior of these probabilities in the inhomogeneous case. Okay? And this is joint work with Dmitry Dolgopyat, and this part of the project is published. Okay, so this you can find. Okay, so before I give you our results on this problem, I would like to just look at it a little bit from afar and identify some features of the setup that we need to pay attention to, because they have to shape the result. Okay? So, important features. Features of the setup. Okay, so the first thing that I would like to say is that inhomogeneous Markov chains, that's a very, very general class of Markov chains, and it's very, very easy to cheat with them. Okay? If I want, because I have the freedom of choosing different state spaces and different transition kernels, by manipulating the probabilities and choosing them very, very close to 0 and 1, I can simulate any non-stationary deterministic process that I want within the setup. Okay? So I don't want, no theory is going to cover all this scenario. So I need to add assumptions on the transition kernels that prevent me from lying this easily. Okay? I'd like to work harder to lie. And basically what we need is we need something that will guarantee mixing. Okay? So I'm going to tell you what is the structure of the Markov chain that applies to the setup that we are interested in that guarantees mixing. Okay? It is the following condition. It's called the Deblin condition or uniform ellipticity condition. And I will just tell you what it is, and then you can forget all about it. All our state spaces are going to be finite and with bounded number of elements. This is because the state spaces in our case are going to be the Markov partitions of the automorphisms. I'd like to remind you that there are only, although there are infinitely many automorphisms here, they all fall into finitely many types. Because let me remind you some fact from the previous lecture. The derivative of each of these automorphisms is the product of n0 matrices with entries which are bounded. So there are only finitely many types of automorphisms, and therefore there are only finitely many types of Markov partitions, and therefore there is a uniform bound on the number of terms.
Can you tell me what is mixing in this case?
I will. Okay. The second condition that I want to impose, I don't want to have probabilities arbitrarily close to 0 and 1, okay? So I'm going to impose the existence of a constant epsilon 0 such that either the probability is 0 or it's bigger than epsilon 0, okay? And the third condition, that's not the classical Deblin condition, but that's the one that applies in our setup, is that if for any step at time n, and for any state at time n, and any state at time n plus 1, I can find a way to go from this one to this one through an intermediate state. Okay? This is 2, and this is 1. You understand what I mean? You take an arbitrary state at time n, an arbitrary state at time n plus 2, you can jump from n to n plus 2 through some intermediate state at time n plus 1. So this is step 2 Deblin condition. Okay, so it's not exactly a full shift, but it's not very far from a full shift. Louder? What?
On the line C, the second, the last one is Pn plus 1. Right?
Yes, thank you very much. Yes, absolutely, thank you. Okay, now, the reason I'm telling you this condition is that I want you to see that it's a condition on the transition kernel. So if I understand the Markov partitions of each automorphism, I can check it. Okay, and this is indeed what we do. But now let me tell you in what sense it implies mixing. It implies row mixing. So it implies that, sorry, I cannot bring this, okay, maybe it's clearer now. It implies that there are global constant C mix, positive constant, and some theta between 0 and 1, that the correlation between what happens at the time n and at time m decays exponentially in the distance between n and m. It's like row mixing. In fact, you get a little bit more. Okay, so bounded type goes very, very heavily into checking that the Markov chain that is relevant satisfies this condition. Okay, so this already uses a bounded type. Okay, second thing that I would like, where's the, I'm looking for the erase, here it is. Okay. Okay, so we need to add to our setup some assumption on mixing.
For which function does the mixing operation?
L2. These are finite sets, so yeah, bounded. Okay. Second thing is the following. I have a process of jumps, okay? maybe you remember from your probability classes that if the functions are bounded, you have the CLT, but if the functions are not bounded, maybe you have other distribution limit theorem, Cauchy, things like this. I don't want to deal with that. So I'm going to assume that all my functions are uniformly bounded, okay? So, of course, the real condition should be something weaker that guarantees the Gaussian domain of attraction. But in our case, because we're talking about the jumps of automorphisms, and there are only finitely many types of automorphisms, the jumps are going to be bounded. So that's good enough for me. Okay, but now comes something which is much more delicate and interesting. There are arithmeticity problems. So what are the arithmeticity issues that are so essential to the study of the local limit theorem? Imagine that all our jumps are divisible by 2, but our target is odd. Well, then this event ain't going to happen, okay? So we have to prevent scenarios where these random variables are always constrained to be either in a proper subgroup or in a coset of a proper subgroup, okay? So this is called the lattice obstruction. But the problem is that there is something much more subtle than this that could also happen. And this is very familiar to anyone who has used the local limit theorem in dynamical systems. Imagine that all our you know what, let me just say here co-boundary phenomena and give you the detail later. Because the question, what is exactly the co-boundary phenomena that can give trouble, is an interesting question. We'll talk about it a little bit later. I'll just tell you briefly what could happen. You could have a sequence of functions, fn, which are not constrained to a proper subgroup, but if you subtract from them a co-boundary, they are. And the co-boundary, when you add it up, gives you telescopic sum which doesn't grow. So it just smudges you a little bit away from the lattice without actually putting you far away from the lattice. So we will talk exactly what this means later, but I just want you to remember already from the start that when you're talking about sums for Markov chains, there are co-boundary issues that you need to take care of. If fi itself is of the form ai plus 1 minus ai, the sum is going to be telescopic and maybe it doesn't go invariance. Okay, so we need to deal with this. Okay, so last thing that we need to pay attention to, not almost last thing, is we need to guard ourselves from silly things in the following form. We have here the sum of functions which depend on n. What if the sum converges? What if the sum is eventually 0? The terms are eventually 0. So we want the variance to go to infinity. Okay, so we want the variance to tend to infinity. Now, all the results I'm going to tell you about today are going to deal with these issues by assumptions. We're going to assume these things. But then, of course, we will assume them for the general results on the local limit theorem, but then, of course, there is the work of checking these assumptions for our particular setup. I'm not going to talk at all about this part of the proof simply because I don't have time. But this is where the work enters, checking. Maybe if I'll have time, I will explain how to check the co-boundary condition, but probably I will not have time. Okay, so these are the first couple of things we must pay attention to when we think about the local limit theorem. Now, there is another thing that we need to pay attention to, and it is the behavior of the target, the growth of the target. How fast does the target move? Now, it is customary in this business to distinguish between several regimes where these probabilities behave in different ways. So the first regime is what's called local deviations. This is the classical regime for the local limit theorem, and it is the scenario when Zn star, the target, minus the expectation, is big O of square root of the variance. The classical local limit theorem is exactly at this, in this case. Another regime, a little bit more general, is what's called moderate deviations. And this is the case when the deviations are little o of Vn. So they could go much faster than the square root, but still I want them to be negligible compared to Vn. Then comes large deviations. But I'm going to divide this to two parts. Admissible large deviations, which I'm not going to define formally now. Part of the problem is exactly what should you assume here. I will just tell you that it follows from, so definition later. I will just tell you that it follows from the assumption that Zn star minus Esn is less than a constant times Vn for C not too large. The question is, what is not too large? Okay? And finally, we have the remaining cases. Non-admissible large deviations, where this condition, which I did not yet specify, does not hold. Now, I want to stress that, unfortunately for us, all four regimes are important for us. When you analyze the case of square root of 3, you find yourself in the regime of local deviations. But when you analyze the case of non-admissible large deviations, the worst possible scenario, well, this is relevant for square root of 2. Okay? Suppose I chose my point randomly uniformly at this rectangle and started to apply my contracting automorphisms. I would get some random target Zn star. Do you know what's going to be the regime, the typical regime for Lebesgue almost every point? Moderate deviations. This is the almost everywhere case for x plus n alpha. If you choose x randomly uniformly and you ask what happens when you analyze the local discrepancy functions for this sequence, you will be in this Zn will behave like in moderate deviations, but not like in local deviations. And this scenario is also important because this is exactly what happens when you have exponential local bias. So I remind you that apart from the Lebesgue measure on the staircase, there are other ergodic invariant measures discovered by Hitoshi Nakada. The typical behavior of points for those measures is admissible large deviations. So we really need all, we really need to understand all, okay? Now, the situation with the general local limit theorem for inhomogeneous Markov chains is as follows. There is a general universal theory for the first three cases, which I will describe today, but not for the fourth one. For the fourth one, you have to do ad hoc analysis for the chain that you have, okay? And I will not have time to explain to you how to do this for our chain because basically I did not really tell you what our chain is in details, okay? So I'm only going to talk about the first three cases, but I want to emphasize the fourth case happens for square root of 2, okay? It cannot be ignored. Also happens for square root of 5. No, sorry, square root of 2. Doesn't happen for square root of 5. But it happens and it needs to be understood. But we cannot do it using general theory. It's highly non-universal, okay? So now, let's start talking about the problem. And you see, the way that I stated it, admissible large deviations is the most general scenario. So basically what I'm going to do is I'm going to give you a definition of what is admissible large deviations, and then I'm going to state the local limit theorem in this case, and then I'm going to derive the local limit theorems for local deviations and moderate deviations and special cases. Okay? But before I do this, I must tell you now what exactly is the condition you need to make to avoid the arithmeticity obstruction. Okay? So let me state this condition now. I'll do it here because I want to keep it. Depending on how much time we will have, maybe I'll show you how to check this condition, but most likely not. But you can, this part was published, you can find it in the book. Okay, so I'm going to call this the irreducibility assumption. So definition, Fn xn is irreducible. In the Givash-Hardy work, this is what corresponds to the aperiodicity condition, for those that know what I mean. If we cannot, okay, negation, cannot write Fn xn almost surely in the form Fn is Gn plus coboundary An plus Hn, where Gn, xn, xn plus 1, these are all functions of two coordinates, always takes values inside some proper lattice. Independent of n. This is a non-stationary coboundary. So it's a function of the form an plus 1 minus an xn. And hn is a function such that their variances are summable. And all are bounded. So Gn, Hn, and the transfer functions are uniformly bounded. First, I'll talk to those of you that remember the aperiodicity condition of Givash. The aperiodicity condition of Givash, which is the condition that applies for homogeneous Markov chains, is that the function is not equal to another function taking values in a proper subgroup plus a coboundary. Here we just have an additional term, Hn, such that the sum of the variances converge. Of course, in the homogeneous case, everything is independent of n, and such a sum cannot converge without being identically zero. Okay, so this is a non-stationary effect. Now, let me remind you the 3-series theorem, or 2-series theorem, I never remember, which also applies in this case for Debelin chains. If you have, if the sum of the variances converge, then the series, the pointwise series of Hn minus its expectation converges almost surely. So when you look at this part of the expression, this is up to modification by constants, the expectations. This is summable almost surely. And this is a telescopic sum, it remains bounded. Okay? So if we had such a decomposition, then what would the distribution of Sn look like? You would have, you know, the group Pz. Okay, so this would be 0, P, 2P, minus 2P. Think about P being 1,000. Okay? So this term would be constrained, the sums of Sgn would be constrained to lie on this lattice, okay? And then we would have this noise. This has finite variance. This is finite, it's bounded, so it's tight. Okay, the distributions are constrained to a compact set up to small mass. So basically, these things would, they would make a fuzzy perturbation that can move you locally with high probability. But really, what would happen is the distribution, although maybe it will not be supported by PZ, it would be concentrated near PZ. Okay, if I look at the distribution of the sum of Sn, maybe it will not lie on the lattice, but it will concentrate near the lattice. That's very bad for the local limit theorem because there is nothing universal about the way it is concentrated near the lattice. And it would bring non-universal effects into the asymptotic expansion. Okay? So this is why we need to rule this out. So this is the version of the Givarch aperiodicity assumption in our setup. Okay. Any questions? Now let's start talking about the local limit theorem for large deviations. We have already seen it in Hannibal's talk. I think it appeared implicitly in Richard's talk. And I will just remind you that standard large deviation theory says that if you want to understand large deviations, you have to look at what probabilists called log moment generating function, and dynamicists called pressure. You need to pass to the Legendre transform. In probability theory, it's called the rate function. In dynamics, it's called the entropy function. And the rate function gives you the asymptotic analysis. So we will do something similar here. Okay, so let's start first with this, with the log moment generating function, the pressure, and its Legendre transform. And rate function. Okay, so what's the log moment generating function? It's Fn of t, 1 over the variance of the sum, log E of Sn. No, not E of Sn. E of Sn. That's the log moment generating function or the pressure. It depends on n, okay? Notice that this is a finite, convex, real analytic. Of course, I have to assume that the variance is not 0. I forgot that. Yeah, we have to assume the variance is not 0. But we even assume that it tends to infinity, so that's okay. If the variance is not 0, then it's actually strictly convex. Okay, so think about the convex function. In Anthony's talk, he talked about the behavior near the asymptotes. Remember this. Okay, now we're going to take the rate function, which is the Legendre transform. That's going to be the Legendre transform. So what is this? This is S times t minus Fn prime. Question? Okay. For the unique t such that Fn prime t is S. And there is a variational, this is actually the solution of a variational principle. And for this reason, this function is closely related to the a function which measures the entropy of the equilibrium measures along a certain one-parameter family. So this is how it appears in dynamics. Of course, I'm making an assumption here that such a T exists. Yes?
Maybe it's not Fn prime, it's just Fn.
Oh, absolutely. That's right. Here it's the prime is there. Thank you very much, Emilio. No, this didn't really work, right? Okay. Now comes the important point. We have asymptotes. Okay, let's call the slope of this asymptote Fn plus infinity, Fn prime, and let's call the slope of this asymptote Fn prime minus infinity. We are not going to, because it's convex, the slope is monotonic. We are not going to be able to solve this equation if S is bigger than the right asymptote or smaller than the left asymptote. Okay, we can only do it if it's in between. So this is well defined on a finite domain. On, so Fn prime minus infinity, Fn prime plus infinity. By this I mean the limit of the derivative as you tend to infinity or minus infinity. Okay? Good. So now we have a problem because everything here is non-stationary. These functions depend on n. Okay? In the classical thermodynamic case, this function converges to the real pressure function, and this function converges to the real Legendre-Fenchel transform of that function, and there is one function to worry about. It converges. But here there is no reason for it to converge. It depends on n, and there is absolutely no reason for it to converge. However, luckily for us, there is some control. So, but I don't have time, so I will not tell you what is the control of F, and I will only tell you what is the control of In. Okay, so here is a theorem. Okay, let's make a notation. No, I want to keep this notation where you will see it. Okay, I will write it here. So I'm going to define intervals. A and R, B and R is going to be Fn prime minus R, Fn prime plus R, and of course I'm thinking of positive R. And the theorem is that if Vn tends to infinity, then for all R, In is well defined and uniformly, strictly convex on A and R, B and R. It's a moving interval. Lucky for us, there exists a CR positive such that A and R, B and R, all these intervals, starting from some place, contain some interval. In fact, they contain an interval that is centered around this quantity. No, I'm not writing it correctly. Sorry. Such that for all n bigger than n0. So the domain, what I'm writing here is that the domain of these functions, although it depends on R, its length is bounded below. And thirdly, there exists NR such that in BR such that for all n bigger than nr, we have the following uniform estimate. I have to assume doubling condition, sorry, that's very important for this. So what's written here is the following statement, that we do have control of the shape of the rate functions. The minimum is, okay, it's moving. It's basically the normalized expectation. But it's strictly convex. And what's important is that there is some constant which does not depend on n, this CR. Okay? Where it's basically a parabola. Which parabola? This parabola. Okay? Okay, so we do have control of the rate function, but not on the entire domain, on a bounded interval. And now I'm ready to define admissible large deviations. So definition. Zn is admissible if for all actually, this is true on compacts. Okay. Let's do it on this interval. In fact, it's for every compact I can get this. For all s such that s minus okay. And moreover, I should tell you that BR, sorry, no. Yeah, on R, on an interval of size R. Moreover, I want to tell you that BR tends to 1 as R tends to 0. So if you want to move very, very close, this is R. So if you want to move very, very close, then the approximation becomes very, very good. Sorry, that was a very good question, and I confused you. The interval where the approximation holds is minus R to R. If you take a short interval, then the multiplicative error tends to 1. Okay, so Zn is admissible if there exists R such that Zn minus Vn is inside actually, let's write it in a quicker way, such that Zn is Fn prime Cn for Cn less than R. In particular, if e.g. Z minus Esn is less than Cr divided by Vn is less than Cr Vn. Okay, so when I told you that large deviations is when it's less than a constant time Vn, for C not too large, well, this is the C that is sufficient. Okay, so now I can finally state the theorem. Assume Deblin Fn is uniformly bounded, integer valued, and irreducible. Then for all Zn in Z admissible, we have admissible, we have that the probability of Sn is Zn star conditioned on the last state, doesn't matter what you use to condition, is 1 plus little o of 1 over 2 pi Vn. Vn is the variance. It turns out that irreducibility implies that the variance tends to infinity. But you can add the assumption if you don't want to trust this, times e to the power minus Vn In Zn star Vn times an error term where the error term is bounded away from 0 and infinity on compacts uniformly in N. And it tends to 1. It tends to 1. Sorry, as t tends to 0, uniformly in N. Yeah. Okay, so basically, yes, yes, 1 minute then. Okay, so this is the asymptotic expansion. I'll just say very quickly that corollary, in the case of local deviations, so if Zn minus the expectation divided by the square root converges to some finite limit, then these probabilities are asymptotic to 2 pi Vn square root e minus 1/2 c squared. That's the classical statement of the local limit theorem in the regime of local deviations. And in moderate deviations, half a minute. If you use this asymptotic expansion close to 0, close to the minimum point, then these probabilities are asymptotic to e minus Vn In Zn Vn. And this is, if you want to to simplify it a little bit, it's e, it's not 1/2. No, it's not 1/2. So you have 1 plus little o of 1 over 2 Zn minus the expectation divided by square root of Vn squared. Okay, so I just wrote down the semiotic expansions, and now I will finish because Nikolai is getting upset. So thank you very much.